Thank you. Okay, thank you. Can everyone hear me okay, more or less? In the back, maybe I'll have to walk over here. I don't have the distance clicker, so I'll have to be sort of tied to my computer. That's not working, but I'll try to project. So thank you for the invitation to come here to IRES. It's quite a privilege and honor to come here. I've known about the program for some time. Way back when I applied as a master's student to come study here. That didn't quite work out, but I'm glad to be here to speak to the crowd. I know there's a lot of expertise on the issue of ecosystem services and some of the topics that I'll be discussing, so I look forward to feedback on that. As mentioned, I recently was appointed as an assistant professor at the School of Community and Regional Planning, and let me just take advantage of the forum to give a plug for SCARP. I see that there's a lot of overlap with interest in IRES. Obviously, there's a few faculty members that are jointly appointed, Stephanie Chang and Tim McDaniels. And my sense is that there could be a lot of really great, interaction, and it'd be wonderful to see more IRES students over at SCARP. There's a lot of interesting things going on. Actually, Magid Senbelt, who's here in the audience, Magid, if you want to raise your, Magid does excellent work in urban design and climate change. His class is highly subscribed and has received wonderful ratings from students, so I'd encourage students to check out some of the work being done there. And also tomorrow, Bill Reese is giving a talk. Bill Reese, who, for those of you who aren't familiar with his work, was one of the developers of the idea of the ecological footprint. He's giving us a talk tomorrow at 12:30 over at SCARP, and the title of his lecture is a little bit more optimistic. It's "What Can We Do?" So I think it'll be in a positive light. So hopefully, or that may interest some of you as well. So the talk today, I will present some work that I've done in stream restoration in the Barcelona metropolitan region. That will be where the focus of the talk will be. But I also wanted to leave a few slides at the very end to talk about some of my work in forest conservation, since that's the direction of where my research will be going, in collaboration with people like Kathy Bayless, who's also in the audience there, and so maybe if she wanted to add about what some of the work that we're doing. So the focus will be on the stream restoration, but I'll have a few words for forests as well. So the title is Examining the Demand for Ecosystem Services, the Value of Stream Restoration for Drinking Water Managers in the Llobregat River, Spain. And first, just an introductory slide of what ecosystem services are. I know there's a lot of expertise on this topic here at IRES. As a graduate student, I read a lot of the work from scholars coming from here. But for those of you who may not be familiar with the term or less familiar with the term, here are a few common definitions of what ecosystem services are. The most simple definition is that they're simply the benefits that people derive from ecosystems. More specifically, you can think of the aspects of ecosystems utilized actively or passively to produce human well-being. So the idea is that ecosystem services is trying to link economics or studies of human well-being with ecology and ecosystem processes. And that space in between is largely what ecosystem services is trying to build better bridges. So when I was developing my research as a graduate student, there was a lot of excitement about this idea of ecosystem services as a metaphor, as a potentially interesting idea, but yet its application and practice had been still quite limited. And since I was in a planning department, and part of what planners do is bridge knowledge to action, I was thinking about how do we actually operationalize this idea of ecosystem services with specific users, right? How do we actually have, how do we bring this idea into the decision-making bodies, into the institutions that are actually deciding how to manage these resources? And if we're not able to do that, then it will just stay as a metaphor, an interesting idea, but it really won't translate into change. And what I noticed is that a lot of the research on ecosystem services was really focusing largely on the biophysical aspects, examining very carefully how the biophysical processes were working, and then trying to attach some numerical value to what those biophysical processes were doing. The software Invest, which some of you may be familiar with, largely does this. It essentially, on a watershed or landscape scale, looks at the values per pixels. What's the carbon storage value of this pixel on this area? Or what's the water producing value per pixel, right? And so my sense was that it was producing very interesting maps, very colorful maps, but just asserting, just claiming that certain dollar values are attached to certain areas wasn't enough to really, you could catch the attention of decision makers, but it really wasn't enough to make sure that those were included into decision making. And so my thought was that we should really instead first talk to the resource managers first and see what they're interested in, and inverse the sequence of, instead of studying the biophysical first, to first study the decision making processes. So I attempted to do this in the watershed that provides a large part of Barcelona's drinking water supply. The city of Barcelona and the metropolitan region is about 3.5 million people. They largely depend on this river. So here you have a good case where you have human dependency on this ecosystem, the ecosystem here being the river. And when I arrived in 2009, they had recently installed desalination technology at the two surface water treatment plants where I was studying. So one here and one here. And they installed this technology simultaneously to comply with drinking water standards. They were not able to meet water quality standards without this technology. And I thought, oh, well, my first reaction was, oh, goodness, this is sort of the opposite of the New York City watershed case, which for those of you familiar with ecosystem services, you've probably heard about the example of New York City is sort of the stellar example of what ecosystem services, because they invested in their watershed in the natural capital, and that way they avoided the investment in the technology, and it's sort of the case that's cited as ad nauseum. And here we have the opposite case. We have a highly degraded watershed where they've already installed the technology. And what this, and I went and I worked at the treatment facilities for several months at one, several months at the other, to really get a sense of how they are making decisions and what their decisions rule were on when to use this new technology and when not to. And what that protocol was, or what the decision rule was that as temperatures rise in the summer, they will add additional desalination modules. And every time they add a desalination module, they need to spend 1,000 euros per day more. So their decision rule then creates a clear link between the ecosystem well-being, in this case, stream temperature conditions, and economic costs, right? So, How is it degraded? Why is it getting salted? So it's getting salted because of mines here, potassium mines, which release, in addition to sodium chloride, also bromine. And bromine, when combined with organic matter and combined with chlorine, which they put to disinfect, creates what's called a disinfection byproduct. And the warmer the temperature, the more disinfection byproducts are created. And so, because it speeds up this reaction. So in the summer, they're not complying with basic health standards. They're in compliance. So they need to get rid of the salts and the bromines in the surface water. And so that was the regulatory reason why they had to include this. So that's just a picture of the treatment facility. The river flows in this direction. Here's where they actually pump the water up into the settlement tanks with the coagulation and flocculation process. And then this empty space here is actually where this is an older photograph. So this is where the desalination modules are. And this is the large, huge storage tank. And it then goes out to the city of Barcelona and the metropolitan region. Maybe this will give some idea to what the watershed looks like. It's highly degraded in the mid and lower parts. It looks great in the upper parts where it's the Pyrenees Mountains, but it's very urban. It's so urban, and there's infrastructures. There's the high-speed train going here. They actually mow the river. At the infiltration point, there's an aquifer below, and because of the chemicals and the oils, they get into the sediment, and it prevents groundwater filtration into the aquifer. So the water company pays for someone to mow the river and lift up the sediments to increase infiltration. So here's what temperature looks like at the entry of the treatment plant. That's the value that we care about. We care about what the temperature is when they capture the water. And the red line, so we have stream temperature on our y-axis and time on our x-axis. As stream temperatures rises, the 2009 data, when they cross certain thresholds, then they begin to add a new module. So that's the decision rule, right? After 12 degrees Celsius, they add another module. That's one module. Then when it hits 14, they add another module, right? So as you add each module, you're incurring more expenses, right? The idea is, well, what if we were to actually reduce stream temperature, have cooler water, then we would avoid passing these thresholds. We would avoid having to add these expensive desalination modules. And there are also, of course, ecological benefits to restoring stream temperature. High temperatures reduce the ability of streams to have dissolved oxygen. So there's a lot of fish kills in summer months when there are very, very warm temperatures, and there's not a lot of dissolved oxygen in the stream. Stream temperature also inhibits reproductivity of fish and other species. So high stream temperatures is really symptomatic of urban streams. So it's common to have unusually high stream temperatures. So here we have a good alignment of ecological objectives with the specific economic objectives of these specific water treatment managers. So the question was, can the restoration of ecosystem structures and functions influencing stream temperature provide valuable ecosystem services for water treatment managers? And in the restoration that we were going to look at specifically was the restoration of riparian forests. These areas are degraded in terms of the ecosystem structure along the riparian corridor as well. Here we can see two contrasting examples. Here there's no riparian forests, and so the amount of thermal radiation entering the stream system is much higher. And here you have an example of how what riparian forests can do in terms of shading services. So our question is, well, how much could this potential shading reduce stream temperature? And if it does, how would that reduction translate into dollar values according to their own treatment protocols? And actually, that's an important point. The valuation process here isn't being done by some sort of contingent valuation or any other sort of assumption. They're telling us what the value is. They're saying, for us, it costs us $1,000 to operate this module. So we say, OK, fine, that's how much it costs you. So we're really, the valuation numbers here are really on their own terms. So fortunately for me, stream temperature modeling is not something that's overly complicated, something that someone who I don't consider myself with a modeling background could perform. It's essentially a temperature budget, or an energy budget, excuse me. The result of the temperature is how much energy comes into the system, how much energy goes out. Thermal radiation direct thermal radiation from the sun is a big part of what goes into the stream system. And the stretch that we're going to model starts about 60 kilometers or 57 kilometers upstream. There's one major tributary here that inputs into the system as well. And our endpoint, what we care about, is what the stream temperature is at the water treatment facility there. That's what we want the model to be able to predict. Because if if it successfully predicts what the temperature is going to be here under various discharge conditions, meteorological conditions, whatever, we'll then be able to alter how much shading is up here, and then see how much that shading will change stream temperature. Right? So the model was already created. It's something that was developed by Fish and Wildlife Services, later available by USGS. There's some great training programs online that I was able to do to figure out how it works. The data inputs are reasonable. You need to understand what the hydrology conditions are, right? How much water is going into the system. You need to figure out what the geometry of each stream segment is. You need to understand what the meteorological conditions are, which I got from a weather station, and then the shading conditions. What's the topographical shade and what's the vegetation shade? It assumes constant mixing. And a question I often get is, what about groundwater? It does allow you to put in the temperature of groundwater. although it does not do more sophisticated things like hyphoreic movements, right, where water goes in, up, and out of the water. So it assumes sort of uniform mixing of the stream temperature. Okay. This is what the model looks like in sort of nodal form. So for each segment of the stream, you describe what its orientation is, you describe what its topographical shade is, elevation, et cetera. There are also a couple wastewater treatment plants that discharge into the system here. So we were able to get what the temperature was and the volume of that discharge into the system as well. So for the restoration scenarios, first I did all the field work to figure out what percentage of each segment has shade. And then some were actually quite well. You know, some street segments already had good condition of riparian forest. So we didn't want to, so we sort of excluded those as potential candidates for restoration, right? Other areas were excluded for potential candidates for restoration because, you know, it was a cliff or there is really stony and the soil conditions weren't appropriate. So we really, when I go over the different scenarios, we're really in a sense being conservative or only looking at areas that are candidates for possible stream restoration or investment. And so these are these red areas here. And areas with over 30% riparian forest were excluded. So this is how the model performed in comparison to the predicted or the observed temperatures. So again, we're sort of hiding the real downstream temperature from the model, sort of behind our back, and saying, okay, on this day, this is the amount of stream flow. This was the air temperature. This was the humidity. Tell us, can you predict what that temperature will be at the bottom of our segment? And this is how it did. The dotted lines is the model, and the black is is observed. You can see the observed that has some gaps. The gaps were bigger as we went further back in time, which prevented us from using a larger data set, which was unfortunate. You can see that it over-predicted a bit, especially at the lower temperatures. So this is the modeled versus observed. You have a large over-prediction of the stream temperature down here, which is less important for our purposes because we're only interested in what happens above 12 degrees Celsius, right? Because that's where you start adding modules. So at colder temperatures, we're less concerned about this over-prediction. So this is what it looks like as on a day-to-day basis. On our x-axis, we have distance upstream. So 0 is the water treatment facility. This is the temperature we're interested in predicting. This is the 57 kilometers upstream, so this is a starting point. And here we're looking at the different scenarios. So the black is observed. This is as the water flows downstream, right, as it goes to 0, temperatures rise, right? And that makes sense. It starts off really cold in the mountains, and then temperatures start rising as it goes downstream. So this is the general trend in all the scenarios. The black dots are observed, so this is sort of what sort of really happened. The green dots are 2 of the restoration scenarios. So as expected, you add more vegetation, you reduce the amount of thermal heating, and the temperature drops, right? So you have less, you have a smaller or lower temperatures. The red X's are without any vegetation. So we also looked at, well, what would happen if we just got a chainsaw and just took away all vegetation? How much would temperatures rise in that scenario? And as expected, this is what the rise in temperature was, right? So on this day, and of course I picked a day that it was good for the example. On this day, this restoration scenario made a difference, and they would stay 1 module under because they're under that 20 degree Celsius threshold from adding another module. Now this didn't happen on all days, right? On some days, the threshold was somewhere else, and it made no difference, right? But on this day, in these 2 scenarios at least, it made a difference, and the facility did not have to add a new module, and so for the vegetation actually saved them money, right? And on some days, sometimes this would add additional modules. They'd actually have to add more modules because of if it didn't have vegetation. This is just a summary of the temperature changes. So as you restore, you have cooler temperatures. As you eliminate vegetation. You have warmer temperatures over time. This is the extreme. This is a case, so this is 100% restoration. We just use that as an upper boundary, as an estimate. It's not a realistic number at all. We wouldn't expect. Yes, John.
I don't understand what kind of restoration you're talking about. Vegetation, just largely, but
Yes. I have a couple pictures here. There's a lot of invasive cane species along the stream, and the part of the work is to get rid of that cane and then add in trees. So in that one slide, native tree species. No, not any changes in sort of directional, sort of geomorphological. No, that would be the other work which you could do if you increase discharge. Yep.
Slide before, I want to.
Yeah.
Just before you start adding
More dots.
more dots,
Yeah.
have a jump.
Yes. Exactly.
Is that a wastewater plant or something?
Good question. That's the tributary. That's the main tributary that, in this case, was coming in warmer water. So we have a measurement before and after, and boom, you see a clear jump. On other days, it can be a drop.
Do you have a larger effect when you have trees and it's cold? So than if you have nothing?
So that's an important point. There's definitely less of an effect in this part of the stream than in this part of the stream. That suggests that the value of shading is greater here. Temperature is rising faster in upper parts of the segment, and so that's where there's more value in adding.
Yeah, I was thinking the effect of something happens between those 2 points, and it's something.
Right. It's the tributary that's entering the main segment.
The effect of the tributary is larger when you have coverage. The difference between the jump is larger, gets larger and larger.
Right, as you go down. The effect, so I guess.
Jordi, I think I'm getting confused. The gap between the dark green box and the red cross at 50 kilometers upstream is smaller than the gap at 0.
This gap and this gap, yes.
It suggests that shading is more valuable downstream than upstream, right? Because your gap is changing,
sorry.
your gap is increasing. So shading is more valuable downstream than upstream. Then
Well,
there's a separate question.
Can I?
No, I mean,
I think shading is more valuable here because once you shade here, you can't. Well, the gap between, which it depends which gap you're talking about, but
between the bottom, which is 100% shading,
right.
and the green and the red crosses, which is no shading. But that absolute temperature gap is over a degree centigrade at 0, and it's half a degree centigrade at 50.
Right, but you're already on. But what prevented it from rising was here. What prevented it from rising happened up here already. So this is where the rise happens.
And only provided shading 40 kilometers upstream, what effect would you get downstream?
Say that again. If you ran the model.
Only ran the model
Mhm.
with shading up to 40 kilometers upstream, but no closer. You don't provide any shading at 40
Right.
kilometers and closer. What would the effect be at the other end?
Well, you've had a gradual increase and then no shading, and then it would go up. It would rise.
No, you should model it.
Okay.
Okay?
Well,
And the answer to Gunilla's question is really in the fact that your tributary is coming in and raising the temperature because it is a warmer body of water.
right. In this instance, right.
Now I actually want to take you to the next slide.
Okay.
Interesting.
I had a hard time sleeping last night, thinking, who's going to ask me the harder question, Hadi or Kai? Okay.
So here, are we planting deciduous trees?
Yes.
How do they provide shading in January?
Yes, there is still shading. But in January, we don't care about January because January we're only interested in this period. So deciduous trees doesn't affect what's happening because we only care about October to March when it's operating. So yeah, deciduous is not relevant.
To get people like me off your back,
No.
don't show stuff before it. And don't show stuff after leaf drop.
Yeah. But I'm convinced you on that point, though, right?
No. It's not relevant to the decision. I accept that point. But I don't like your simulation because you didn't drop leaves. The reason the size
Right.
of the decrement is smaller is because the sun is lower in the sky. So you're getting more natural shading from all that stuff like that, right? But your trees are still leafy, which is the wrong simulation.
For here.
Yeah.
So this was just it would just be lower here.
Yeah, it would
It would-
be the natural shading from the landscape.
Right. It would be only topographic shading. Yeah.
That's right.
Yeah. Okay, that's fair. I'll accept that. Okay, so with all the scenarios, you're able to figure out how many days you can actually prevent the modules from being turned on, and so you have the revegetation scenarios, and then you have the no coverage scenario, which actually tells us the value of the ecosystem services today, right now, as they are right now. If there was not vegetation there, if there weren't trees there, they would be operating the EDR modules more often, and then that would have an expense, which is about 79,000 euros per year. So one major limitation of this model was that it just gave us, it's a deterministic mechanistic model, it just gave us a number, right? It didn't have no estimates of uncertainty. So I had to sort of do an ad hoc sensitivity analysis where if you change, okay, well, what if you change, the Manning's N? What if you change relative humidity, et cetera? And I ran these different scenarios and was able to pick the maximum and minimum to see what the range of how the valuation estimates would change. Another criticism could be, well, your results are really driven by where your threshold locations are. So I changed where the decision-making thresholds were. I reduced them all to 1 degree Celsius and redid the analysis. And I even did, I said, well, what if I'm maintaining still linear assumptions here? What if I just choose random threshold values? So I just randomly selected temperature values between 12 and 24 degrees. I ran the model under those scenarios. And also you have very similar results, which really shows that it's the reduction in, if you go back to think back to the temperature graph in 2009, there's always will be places where you're on the margin, right? There will always be places where the small reductions in temperature will prevent the managers from adding up the additional module. So this may help answer John's questions about what it looks like on the ground. As mentioned, the restoration activities are largely getting rid of this cane species, and they're restoring vegetation. Fortunately for me, there was actually the precedent in this work, and they were doing it as part of compliance for the European Water Framework Directive, which requires water bodies to reach good ecological status. So they were doing this work already, which as a precedent was very valuable because it provided cost data, right? Because until now, we've just been talking about the benefits to the downstream managers, but not the costs. So we do have some cost data. Of course, this was during the economic boom in 2006, so everything was very expensive in Spain. It cost them 120,000 euros per kilometer to do this work. I think right now it would be much lower in figures, but anyways, we'll use the higher numbers. And I then did a cost-benefit analysis where, of course, we have these big restoration expenses now up front and almost no benefits in the beginning because you're planting puny trees that have no shading benefits. Those are only obtained 20 years down the road. And so what we find is that we're able to still recover part of the investment costs. Between 30 to 50% of the costs in the restoration can be recovered, but it's not a positive net present value, right? Because again, the costs are all up front, and the benefits aren't accrued until much further downstream, or down in time. So some of the limitations here. it would have been wonderful to have more data and use this, do the model over a larger period of time. The issue of uncertainty was definitely a weakness in the model itself. And in terms of my larger argument about sort of inverting how we study ecosystem services, it isn't in some ways quite reductionist, right? We're only looking at one specific ecosystem service, so that is a fair criticism. Also, this issue of scalability and replicability, right? Can this be scaled up? I mean, that's one reason why the INVEST approach is so popular, right? You just pull the model off the shelf and you can go to any watershed and start studying what the values of those services are. And this is definitely a different approach that may not be as scalable and replicable. Although I would also say it can't just be a coincidence that I had found the watershed where, talking to resource managers, we were able to find ecosystem services that are valuable. So on the other hand, I think that if we do look more at the decision-making processes, there are opportunities to use the ecosystem services approach and provide it as one more option on the table for them to manage their water supply, right? So just a few sort of take-home points. Currently, the riparian forests provide value of 79,000 euros a year. About 40% of the cost can be recovered. And again, the larger argument that I'm trying to make is that ecosystem services are more likely to be incorporated into decision-making if we study the demand for these services. And in this case, it was a very targeted biophysical model that really responded to their needs. It didn't need any sort of specialized software. That the tools for providing them with valuable information already existed, right? The key was understanding what the needs were. So up until then, the temperature, I also wanted to just, before opening it up to questions in general, mention a few ideas on where I would be like to be undertaking my research in the next few years. And it will be largely on forest conservation, looking at where I had done work before going to graduate school. I worked with World Wildlife Fund in central Mexico in the forest conservation program, working with ejidatarios and indigenous communities on community forestry, and also on payment for ecosystem services, a PES program there. And together with Kathy, who's in the audience, we've been working on this idea of impact evaluation and how do we know that our conservation programs are effective? What's the additionality of these programs? A lot of the assessments, especially in the community forestry, they tend to look at all the success stories and then do meta-analyses of those. But there's certain audiences that would prefer other types of evidence, other types of knowledges to prove that those are actually effective policies. So I think there's an opportunity to perhaps work with different methods to see how those policies are effective. Of course, the issue that in program or impact evaluation is this counterfactual. To show that these programs are effective, we need to have better counterfactuals and think through carefully who we are comparing our program participants to. So some of the research questions that I'm interested in is how can we measure the impact of different conservation policies, protected areas, community forestry, and PES. I'm especially interested in looking at community forestry and seeing what the impact of those programs are. And also accounting for community governance, because a lot of these impact evaluations really control for physical features. So when they're looking for their counterfactual, they compare areas with similar slopes and elevation and legal systems, but they're not getting at the governance issues, right? The politics, the social capital, which in many cases is really driving conservation outcomes. It's those communities that do have good governance that are able to successfully protect their forests. It's also been mentioned in somewhat a critical tone that randomization hasn't been used to test the impact of these policies. I think there are also good reasons why RCTs or randomized controlled trials haven't been used, and it's worthwhile exploring and explaining why conservation hasn't applied these. And I'm also interested in perhaps incorporating some of these methods into an existing conservation program. I'm really interested in trying to reach out and see which organizations are interested in using these sort of evaluation techniques to to evaluate the impact of their program. So those are the sort of things that I'm interested in doing. There was recently a workshop held in Barcelona, not a coincidence, I must confess, with some well-known folks in the field, and there'll be and there might be a special issue coming out on that specific topic. So I think there's really a lot of interest, and I hope to be part of that intellectual community in the next few years. So if there's any interest in working on that, I would definitely be happy to talk to people about things like that. So, and with that, I'll open it up. And Jordi, you already had your tough question. Okay. Yeah, Robin? Okay. Right. So, the technological solution is being used. That sort of is there. That is. What I'm arguing is that there's the investment that can be made can be recovered. So investing in restoration you won't recover all your funds for this particular user, but there are also other benefits to restoring the riparian areas that I'm not accounting for. So again, this is a very reductionist view. I'm only looking at what's the value for these treatment managers, but the water agency was doing these projects because they needed to comply with European rules, and there are all these additional benefits, the non-use values to riparian forests. So if you were to include those, then it probably would tip the balance in favor. So, and regarding the technology and I guess what I'm arguing is that the technological solutions are really sort of the status quo. I mean, I was at the treatment plant working with the engineers, and when the suggestion that ecologists and biologists and that a temperature model could help them was sort of scoffed at. And so what I think ecosystem services can do is sort of broaden the types of tools that they have to manage their water. And I think that's hopefully what that's contributed to a little bit, yeah. So it's 20 years, yeah, with a discount rate of 4%, yeah. And again, they could also, if they were to plant bigger trees, they could also improve it. If they were to reduce the cost, I was using cost data again from 2006 when it was very expensive to rent machinery because they were in a huge construction boom. And also the primary cost was really the removal of the invasive species, the cane, which keeps on coming back and comes back and comes back. So the actual just the planting of the trees is really not that bad. It's the removal of the cane which is really expensive. Yeah. Yes, in the back, and then Stephanie. Yeah. Right. So they chose to include stream temperature in their decision-making protocol. First, it's easy to measure, so it's easy for them, the operator, to say, okay, what's the stream temperature? Boom, turn it on. They don't have to go do any more complicated lab work. But stream temperature is what drives the creation of these disinfection byproducts. So when they add chlorine at higher temperatures, these carcinogenic byproducts, which are called trihalomethanes, are produced. And that's what they're in compliance. So higher stream temperatures create these disinfection byproducts. So that's what they chose to use to make their decisions. And that was a key. That was the key to this in large part when I was understood that, and they showed that to me in their decision-making protocol. Well, that's what led me into this work, because that's where the link is between the cost and the ecological system. Yeah. Okay.
So I like the idea of moving to the green side of the equation, but if you do that, it's very hard to figure out what all the demands are. Reduction costs.
Yeah.
So then there's one demand on the site, and that's what we start with. The benefit of optimization is fixed.
Right.
Treatment plant would never invest in restoration.
Right.
The only reason to invest in restoration is for three reasons. One is that it's very headache to have to do this stuff, so really get the site up and out of it. Or two, you went back to supply side things, so you don't have to necessarily go through all this water treatment and everything else and do that supply side analysis, give you a much bigger value for your service. Right? So how do you, so this is actually a good example of the value of looking at the I like the idea.
Mm-hmm.
I'm not clear to me why this is an example.
I'm going to help you this.
Okay, go for it, Hadi.
I'm going to help you this.
Okay, go.
Your analysis doesn't include the capital cost of the machinery that already exists. All you're trying to do is to save their operating costs.
Right.
And so
Yep.
in your cost-benefit analysis, you have a capital cost on the restoration,
Right.
but no capital cost on the water treatment.
Right. Right. So I'm.
To reconsider the decision from a tabula rasa perspective,
Yes.
then you can answer the jump question.
Right, and that's the New York City watershed sort of example, right?
Yeah.
That's when you say, okay, we're gonna the big driving argument for investing in natural capital is that we avoid this huge operating cost. But I didn't have that. I arrived and the huge investment was already made, right?
But over 20 years, you have to replace equipment.
Yeah.
So that should be included in your benefit side, which you haven't included in your cost calculation.
Okay.
Yep.
Right, and that's a whole other issue, right? Exactly. The stream temperatures are going to go.
This is all numerical.
Right, right. You know, I thought the numbers were going to be better for the program. You know, you said it initially the water company is never going to invest in stream restoration. I thought they would be better. They were sort of okay. You know, you could recover 40%, but hey, recovering 40% of a project in an ecological context where the benefits are always quite nebulous and people don't know and they're subsidized, they're paying for it anyway. With the team that found out about this research project that they were just investing in restoration just because that was what they were doing, they were thrilled.
Right, in the sense that if you treat it as the decision maker of the demand side user taking the framework to the food on it, that unless it goes to the side said, right, the internal decision making would not lead you to do this as a
Right, but if the numbers if the stream temperature would have been reduced further, there could have been a stronger case right. On a sort of societal level, yeah. But you don't know that when you're going in, right? You don't know what your results are going to be. Yeah, Leila. Right, right. Mm-hmm. Right. Right. Yep. Yes, ammonium and the nitrification, denitrification process is also another parameter that they're very interested in because when they had high ammonium concentrations in the river, they had to shut off treatment because they weren't able to chlorinate it effectively. So that was another part of the work as well. We looked at how the denitrification process would reduce ammonium levels and therefore also prevent a cost being incurred. So that was the one specific one. Going back to your question on looking at the situation without any water treatment facility. I mean, I was working closely with the water treatment managers on this program, and you know, they were very sensitive. You know, it was very difficult to have access to their facilities. Both of them. One was a public facility, and one was a private facility. And this idea that I would be coming in and writing a dissertation criticizing the desalination was on the table as, okay, well, you know, this is, so that I wanted to avoid, you know, being overtly, you know, critical of that. So, and I think so. Yeah. So working within the daily operation costs, and we met, you know, every 3 months with the operators of the treatment facility to see how the progress was being made. And so the idea was really to provide something useful so that, you know, they could include ecosystem services in their decision-making process, or at least in collaboration with the funding agencies that were funding these sort of restoration projects. And the one question I'll just answer before I'm asked, what happened, right? That's the question that everyone, what happened? Well, the water agency was funding these projects is no longer funding them, since in fact they were reduced, you know, by a huge percentage given the economic crisis. So all projects, all these investments have been stopped and put on hold. The people that I was actually working with, a few of them actually are still there, so they're lucky to still have their jobs. But but in the future, there's now, you know, so they haven't acted on this, but there is clear, tangible benefits that they know of what they were doing in the past, and they hope to return to those projects when there's a normal economic situation in Spain. So, yes.
Other alternatives, is it the most important factor influencing the temperature is cover? Is that what everybody knows, or is it other ways of influencing the temperature? Because heat recovery comes to meet the problem, technical problem with another technical solution, and compare that with maybe ecosystem restoration.
Right. So the other thing that, right, one of the major drivers of stream temperature is air temperature, but there's not much we can do about that, right? So, you know, travel time and sort of meanders and sort of recovering the, you know, groundwater, surface water flows, that was called the hyphoric flows. That also would moderate stream temperature. But shading is really what most managers have done, and they've done this in areas where there's protected for salmon habitats, since salmon require lower temperatures for successful reproduction. So in Oregon, there's legislation that requires certain stream temperature standards. They've included that in their water quality standards, and that's where a lot of this research has come from. And they've done shading experiments and those sort of management practices there. I'm not familiar with other.
Recovering heat from the water to reduce the temperature.
They're shading to reduce the.
No, I mean if you actually use it as an energy source, pull energy
Oh.
out of the water, get it cooler, and you get energy out of it.
Oh, I see what you're saying. Okay, I do not know if there's. Right, and then I see what you're saying. Compare that technological solution to this more natural ecosystem sort of approach. Yeah, I don't know if they've done that. The water treatment facilities are really into energy. You know, the wastewater treatment facilities are really exploring the energy opportunities there with methane, of course. Yeah, Magid? Yes. Exactly. Yeah. Yep.
So I wonder in that case if the tributaries become a factor instead of shading the river, you may be shading smaller tributaries, especially that hall.
Mm-hmm. Mm-hmm. Mm-hmm.
So that would be an interesting sort of.
Yep.
And the other question is about potassium mines.
Mm-hmm.
Are they adding energy? Is the outflow there also relative to what's going into mine operation?
They're mostly adding contaminants. I don't think they're adding any. No, that's all been in the past. They did, but they've now piped it. They put it into a pipe and they dump that into the Mediterranean directly. So, the salt that's coming in is through groundwater flows. It falls on the tailings, and the tailings aren't protected underneath. So it through groundwater flows. That's where you get the salts and bromines. And then the industrial, the day-to-day use, that's just all put into a pipe. Yeah. Yeah, Gerald?
One of the interesting is the idea of natural system providing full services. And I think it's kind of an historic continuing of limitation of the system service to focus on the single service.
Mm-hmm.
I like this idea of focusing on the demand side because it's nice to have control over maybe natural system providing multiple services. And I'm just wondering, given that you can recognize what you mentioned this year, do you have ideas about you considering ways of eliciting multiple services, like the demand for multiple services from individuals?
Mm-hmm. I think that's definitely a good direction to avoid the sort of reductionist trap, right? To not just elicit what one specific, and so they we did do a little bit of work on ammonium, but yeah, my future work is probably going to be more on what I mentioned on evaluating the impact of conservation, and it's moving more in that direction than the ecosystem services. Maybe it's because after writing a dissertation on ecosystem services, you're just so sick of that literature. So I'll give it a rest for a while and maybe come back, revisit it in a few years and see where it has gone. Yeah. Okay.
Do a back envelope calculation to take the water upstream of the warm inflow.
Mm-hmm.
24 million euros.
For
Compared to riparian activity. So one other option they have is to get their inflow water, not from where they're taking it warm, but to take a pipeline all the way up to
Right.
the tributary comes in
Right.
and take the cooler water.
Right. Well, there's even a better proposal, or better, depends which way you look at it. There's the proposal to take it from the dam all the way upstream, right? Which was actually upstream of where the mining tailings are, which makes huge amount of sense from economic purposes. That way, then you'd be like in a situation like here in BC, you just put chlorine in it and you're done, right? No desalination. That proposal was heavily resisted by many of the environmental groups who said that they would be reducing in-stream flows. So politically unviable, even though makes much sense in many aspects.
But it also doesn't force you to clean up the mine.
Right.
You see, if you reduce the in-stream flow and the mines are continuing to pollute, then the river will be in even worse condition. Then you'll be able to impose some kind of pressure on the mine. At the moment, you're just allowing the mine to do whatever the heck they like to do.
Right, and everyone pays for the costs downstream. Yep. Okay. All right. All right, thank you.